Hey Phys 1 kids, Campbell here. In this video, we're going to talk about the problems with friction. Not that friction's a problem, except that, it kind of messes up our idea of the fact that an object can move without a force on it. Let's talk about why friction occurs. Anytime objects are in contact with each other, so when they're on a surface and they're trying to move against that surface, there's a frictional force that opposes that motion. And the reason for that is between the two surfaces, if we could get a microscope and take a look at the surface, we'll see that the surface isn't perfectly smooth. In fact, there are little pockets, and those pockets kind of rub against each other and catch each other, and so it prevents the object from moving smoothly. Now, like I've said before, frictional forces are parallel to the surface because they're caused at the surface of the surface, and they always oppose motion. And there are two types: static friction, which exists when the objects aren't moving. Static means not moving. And kinetic, which occurs when the objects are moving. So static friction is the one that's going to kind of mess with you, because static friction, first of all, we know that it's in the direction to oppose motion, but sometimes that's not a logical direction. So I want you to think about, if there was no friction, what would happen to this object? Remember we talked on Friday about if your feet slid, if there was no friction. So sometimes the direction of the force isn't as intuitive as you would think as it is with kinetic friction. Also, the magnitude of the static frictional force isn't just a constant. We can't just calculate it and it's the same thing every time. It adjusts itself so that the net force is zero and the object doesn't move. So for example, if we take a look at this lady pushing on this box, all right, this looks like a really heavy box. So she starts to push it and the net force must be zero because she's not moving. So the static frictional force must be balancing the pushing force so that our net force, oops, my face is in the way here, so that our net force equals zero. Now, you're trying to push a box, right? So you push harder and you push harder. And so the whole time that you're pushing harder and harder, that static frictional force has to increase so that the box doesn't move, right? If the box isn't moving, then the horizontal forces have to be balanced. So the floor is pushing back with an equal force, but eventually, right, you push hard enough so the box starts to slip and move. So there is actually a maximum static frictional force. And so when you reach that point where you just now slip, you have exceeded that maximum value of static friction. Now, this Fs max does have an equation for it. It's the mu sub s, which is called the coefficient of static friction, and I'm going to talk about coefficients later, times the normal force on the object. Now, the problem with static friction is that because this equation exists, you're going to want to use it, but don't ever use it unless the problem says that the object is at Fs max or that it just slips. Other than that, you always have to do a sum of the forces on the horizontal direction to find the static frictional force. Now, kinetic friction is much easier. Kinetic friction, right, once we've reached that Fs max and the box starts to move, then the kinetic friction is going to be constant. It's that coefficient, this time of kinetic friction, times the normal force. And it doesn't matter if you push the box fast or slow, that force of kinetic friction will stay the same because it's always the coefficient, which is a constant, times the normal force, which, as long as we're not pulling up on the box or pushing down on the box, is going to stay the same. In fact, we could push with enough force that we could move the box at constant velocities, in which case the pushing force would equal the kinetic frictional force, or we could push harder and then the box will accelerate. So the force to overcome static and kinetic friction, you can see that the normal force is in that kinetic frictional force equation, and it's in the Fs max equation. So the force to overcome static and kinetic friction is proportional to the normal force and the coefficient of friction, which is a constant for a surface. Now, keep holding on to that coefficient of friction. I'm going to talk about that in the next slide. But so to find static friction, it's either the force that's balancing the pushing force, or if the box just slips, then I'm at Fs max, where it's the coefficient times the normal force. but kinetic is always coefficient times normal force. Now, there is one thing, if you look at these equations, right, they're all pretty much about the normal force and the coefficient. So there are three things that you need to know that do not affect friction. They are independent of the contact area. Now, I know this seems really bizarre, right? You would think that the static frictional force on this book would be greater if the book is this way on the surface versus straight up and down. But it's still the same weight, right? Regardless of which way I put the book. So the normal force is still the same. But when I put it this way, yeah, maybe I have more force concentrated, but I have a smaller area. Temperature also doesn't matter unless that temperature goes to change the coefficient, maybe make it stickier, like if I start to melt stuff. Also, speed doesn't matter. It doesn't matter how fast I'm going. The coefficient of kinetic friction does not change. So let's talk about this coefficient thing. So it's symbolized by that mu, the Greek letter mu, and it's either sub s or sub k if I'm talking about static friction or kinetic. Now I want you to take a look at these values and compare static friction to kinetic friction. You can see that the static frictional coefficient is always higher. So what that means, if you think about it, right, if Fs max is the coefficient of static friction times the normal force, and kinetic friction is the coefficient of kinetic friction times the normal force. That means that my maximum static frictional force is always going to be greater. So what that means is it's harder to start an object moving than to keep it moving. Also, you'll notice that each topic here, each surface has a different coefficient. And in fact, if we take a look at my book here, I have a Pikachu on my book and my phone with a little rubberized phone case. Now, if I pick this book up, right, as soon as I do that, I start applying a force down the incline of my book, which is due to the force of gravity down the incline, and it's going to start to pull them down. But notice neither of them are moving because right now the static frictional force is equaling the weight down the incline. And so it keeps increasing and increasing and increasing as soon as I keep moving this book up, 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 up. But eventually, oh, there goes my Pikachu. Notice my phone hasn't moved yet. I got to keep going quite a bit to get that phone to slide because they have different coefficients of friction. Pikachu here is hard plastic. He's a little slippery as opposed to my rubbery phone case. So this one took longer for it to move, which means it needed a higher force to get it to go. It had a higher Fs max, which means that it has a higher coefficient than little Pikachu. Sorry, Pikachu. All right, so let's take a look at a problem example. So I have a steel box which has a mass of 10 kilograms sitting on a steel workbench. Our coefficient of static friction is 0.74, which is higher than our coefficient of kinetic friction, 0.57. What I want to know is if I push against the box with a force of 25 newtons, does the box move? Well, first we got to draw a free body diagram. So of course we have a force of gravity down and a force normal up. But honestly, I'm really not interested in those at this moment. What I'm really interested in is what's going on in the horizontal direction. So I have this applied force, which I guess we use that way on the free body diagram. And then I have this frictional force that's opposing my pushing force. Now, in order to figure out the force of static friction, I have to figure out, is this box going anywhere? Does this box move? Because I need to know, is the sum of the forces 0 or is the sum of the forces mass times acceleration? Well, how am I going to do that? Well, to figure out if the box moves, remember, we need to look at our Fs max. All right, our Fs max are that coefficient of static friction times the normal force. And so the normal force, oh, I do have to go to the y direction, don't I? So to find the normal force, right, it is balancing the force of gravity, and since my box isn't moving vertically, that means that the sum of the forces in this y direction have to equal 0. So my normal force must be balanced by that force of gravity. So that means that my normal force is equal to the mass of the box times g. So 10 kilograms times 9.8, which this time is 98 newtons. All right, so we're going to take the coefficient, that 0.74, and we're going to multiply it by 98 newtons, and we get 73 newtons. 73 newtons is greater than our 25 newtons. So I'm pushing with a force that's equal to 25 newtons That is less than 73 newtons. So that means no, the box is not moving, which means then to find my force of static friction, now I can do sum of the forces equals 0, Newton's first law, my object's at rest. So by my free body diagram, to the right, I have that applied force, so that's a positive force. Opposing it to the left, I have my frictional force, my static frictional force, because we know it's at rest. And that's negative because it's to the left, and that has to equal 0. I don't know why it does that. It has to equal 0. So that means that my applied force has to equal the static frictional force. So that means that my static frictional force is equal to this applied force of 25 newtons. All right, so static frictional force is balancing the applied force. It's less than Fs max, which means that I'm at rest. What would happen if I pushed with 73 newtons? So my maximum static frictional force. Well, if we do that equation again, right, if we have the force applied minus the force, in this case, our force of static friction, if we plug some numbers in here, all right, if we apply a force of 73 newtons and my static friction, this in case is Fs max, is 73, I still have a net force of 0. So I'm still not going anywhere, but a smidgen more, maybe is 73.00001 newtons. Now I'm going to start to move. So nothing yet, then I start to move. What, however, if I push with 100 newtons? Well, now I'm much bigger than the Fs max, right? Fs max was 73. So now I'm moving. So what happens? Well, let's write an equation. We're going to need kinetic friction now because we're above Fs max. So, and I'm a lot above Fs max. And remember that Fs max is always going to be greater. So Fs max is always going to be greater than Fk, the kinetic frictional force, because remember mu sub k is always less than mu sub s. All right, that means I'm accelerating. So we've got Newton's second law. So if we write our force equation now, we have that pushing force minus the kinetic frictional force is equal to mass times acceleration. And if I break down my kinetic frictional force, right, that becomes mu sub k times the normal force, and then I just got to plug some numbers in. So I have my 100 newtons minus the kinetic friction coefficient, right, that's mu sub k, times my normal force, which we calculated earlier is 98 newtons. And that's equal to the mass, right, mass, that's my 10 kilograms times acceleration. So we're accelerating, and if we do some more math, we'll find out that that acceleration is 4.4 meters per second squared. Whew, this box is going to start flying. Well, maybe not flying, just moving quickly. All right, that's all I got for you on friction. I'll see you in class.